Okay, everybody, welcome to the April Chemical Consultants Network meeting. I'm Mike Michalzek, the chair of CCN. Chemical Consultants Network, or CCN, is a group of chemists and chemical engineers that provides guidance, expertise, and resources to members who are consulting or are interested in consulting. We are a topical group of the Philadelphia section of the ACS, and we hold monthly meetings. Of course, you're at one of them right now, on topics of interest. And for $35 per year, you can be a paid member and create your own webpage on the CCN website to attract potential clients. So you can sign up to be a member if you're interested at chemconsultants.org. So I want to take the time, because we used to do this during our in-person meetings. If anybody out in the audience now has any information to share on their business, their consulting business, business opportunities for consultants, anything that's of interest to our Zoom audience. If you have a lab and you may want to say, hey, I have a lab of interest, if anybody's interested in some joint opportunities, please put that in the chat on the Zoom. And so the information can be shared to all attendees. I think at the next meeting, we're probably going to have more of a verbal section on this. But I think for this meeting, if you have any information to share to the wider group who's attending via Zoom, please put it in the chat so everybody else can see it. And we can network via the Zoom chat for this meeting. So tonight's speaker, Ron Turi, will be introduced by Dr. Ron Bachofsky. So Ron, take it away.
Okay, welcome everybody to CCN. It's my pleasure to introduce Ron Turi. Ron has a bachelor's degree from Carnegie Mellon University and a master's degree in chemical engineering from the University of Massachusetts in Amherst. He's the owner of a Philadelphia area company called Element 3 Battery Venture. It's a battery research and development laboratory. He has decades of experience with battery research and development, especially with lithium batteries, which are used in electric vehicles, which is obviously a rapidly growing and very important field. He's worked with a number of advanced technology, electric vehicle, battery manufacturing and development companies, and has expertise particularly in advanced silicon-based cell anode materials, as well as inorganic electrolyte solvents for high voltage lithium metal cells and structure electrolytes, electrodes for solid state and lithium metal batteries. He's a consultant for Momentum Dynamics, another local company, which is a manufacturer of high-power wireless electric vehicle chargers. I've worked with Ron on several projects, probably over the course of 10 years, projects which required organic synthesis and brainstorming some ideas. And I've always found him to be extremely knowledgeable and creative. So I hope we all look forward to hearing him discuss. The title of the talk today is The Evolution of Battery Technology for the Emerging Global Electric Vehicle Market. Ron Turi.
Thank you very much, Ron. I appreciate the introduction. That is quite a mouthful. Let me put it on the share screen. And there you go. Is that on now? I don't think so, right? Try that again.
Yeah, I could see it.
Oh, you did? Okay. Try it again. All right, you can see the screen, right? All right, so there's that big long title that Ron put through very generously. I have a lot of things I'm going to be discussing. I've been in the lithium-ion battery industry since 1991, and Ron started to do the math. Don't complete it because it is a long time, and it is a period of time that I think covers an enormous amount of change in the industry, but none so much as we've seen in the last 3 or 4 years. Since 2018, the industry has just absolutely taken off. There was no real belief that electric vehicles would be viable until 2018 when Tesla got out of its so-called production hell. And all of a sudden, everybody said, gee, they hit their 5,000 per week Model S production target when a lot of people did not believe that would happen. They didn't think it was going to come to pass. They also in that year, in 2018, is the year that Volkswagen really came to terms with Dieselgate and used the funds that they had previously allocated to consolidate their vast amount of SKUs and procurement sources into one centralized source. They were going to do that. It was going to cost 6 to 10 billion euros to do that. And they diverted all of that money into electric vehicle production, development, and even EV infrastructure. And yes, part of that was mandated through Dieselgate, but nevertheless, things changed in that year. Lots of other companies became much more serious about designing the right cells that they needed for electric vehicles. So that was really a breakthrough year. And since then, it has just been a ratcheting up, a nonstop ratcheting up of the number of projects that come in during the, before the call came in today, before we started the recording. There was mention about just these ancillary things that come into play when you're making a battery, like polyurethanes and silicon coatings and things like that at the battery pack level. There are also boxes that have to be made in pallets. It is a derivative effect on the entire industry. The ecosystem is going to be huge. It already has started. There's a $7 billion grant opportunity that will be put out with some of the Build Back Better money that was allocated to batteries. And those will be doled out $100 million awards with a main contractor and subcontractors. So these are very serious efforts with lots of money. The growth has just been enormous. And I hope to show you a quick sweep of all of this. So hold on. I'm going to try to go through a lot of these things quickly. And I don't mean to blow over any one area, but if you have questions, if you please we put that in the chat as Ron Bohovsky has requested. The lithium-ion cell, just an overview of it. You have your main electrodes. You have a negative electrode, the anode. You have a positive electrode, the cathode. And these are composites today made of particles that are held together with binders. They have void volume in between. And in between the void is the liquid electrolyte that conducts the ions to complete the circuit. So you have electrons flowing outside of the cell, and you complete the circuit with ions flowing in the opposite direction to maintain electroneutrality. So these are basics. Everybody has their own take on how to explain it, but this is pretty much it. In the middle is a separator, which in this case is just a porous, microporous polyolefin film usually, and it allows the liquid electrolyte to flow through the ions going through the connected channels. And every one of these components plays a part in how effective a battery can be in terms of its energy density, in terms of how much heat it generates, or if it alleviates that situation of generating heat. There are some physical problems that have limits today that haven't been exceeded. For example, it's very hard to make these electrodes very thick. These are things that are interesting to people in the industry and affects the manufacturing costs as well. What's shown here in the anode, this is a representation of graphite and the graphene planes, because that's the most dominant material for the anode today, 1 lithium for every 6 carbon atoms. The cathode can be any number of materials. They're usually these transition metal oxides that are lithiated. And we're going to cover a little bit of that today. There's no way we're going to cover absolutely everything. This is a great source down here. If this document is shared, there is a link to the University of Aachen, which has an entire white paper that breaks down the entire process of how to go from materials to finished cells. And you can see the 3 different kinds of cells that are depicted here. Pouch cells, which are the kind that are being made by LG Energy Solution, for example, for General Motors, and SK is making them for Ford at Blue Oval. You have cylindrical cells. This one is kind of an old-fashioned depiction of one. They usually have terminals on the opposite sides, but Tesla seems to favor round cylindrical cells. And you've got prismatic cells, which a lot of companies around the world are using. CATL, Contemporary Amperex Technology Limited, is one of the companies that's leading in this area, but there are a whole host of companies in this area. I'm going to go through these, not for the sake of going through it quickly, but I just want to show you how these things are configured. You've got these cells here, which are optimized. They have, when I say optimized, it means they try to stuff in as much active material as possible. They're made with lithium iron phosphate by a company called BYD in China. The cells are actually capable of being packed very closely because the material is inherently safer. Lithium iron phosphate, LFP, has a high autothermal temperature. Most other chemistries do not. This is a platform for the new joint venture between General Motors and LG Energy Solution. These long cells that fit in between the split in the chassis, those cells are pouch cells. They're longest pouch cells that anybody's put into commercial production for electric vehicles. There are advantages to on how you get the heat out, many interesting things about how to put it together, but also it's easy to go cell to chassis. We're not going to be building cells the way we were before, grouping them together, putting them to modules, putting them into a box, putting a box of those into a pack, putting the pack into the car. It's going to go from cell directly into the chassis because there's more confidence in the quality of each cell. So that's how these things are coming together. There's a lot going on just on the EV platform. Let's take a look at the market size. And when I say market size, I'm really talking about the cells. What are we talking about? In 2021, 280 gigawatt hours were recorded. And this has been verified by a number of different sources, including IEA.org, the International Energy Agency.org, and all of these estimates that have been done by Bloomberg, New Energy Finance, Avisan, you name it, anybody that's forecasting has been underestimating the amount of production that really took place. And the installed base to produce these things is increasing at a rate which exceeds expectations based on conservative projections, even from the Department of Energy. So everybody's been updating the estimate for this market and making it happen, making their forecasts more forward, bringing them forward to reflect reality. But if you look at it, 280 gigawatt hours, what does that mean? That's 6.6 million electric vehicles. Not every electric vehicle is going to be a big or small vehicle, but the average size today is about 42 kilowatt hours for the electric vehicle battery size. That includes some that are tiny, that are just runabouts, and a lot of those are made for students and younger people in China, for example, target market. But you also have at the other end a lot of 60 kilowatt hour batteries, 90 kilowatt hour and 100 kilowatt hour batteries. If you get a Model S, for example, you're in that realm. And on average, on a global average, it's actually pretty high. This number also includes plug-in hybrid electric vehicles and some hybrid electric vehicles, although the majority of the mix today is full electric vehicles. And this was a surprise to a lot of people who just, have to accept it if you're in the automotive industry. But outside, it's quite staggering. It's $29 billion of cells that were made in 2021. That's the value of the cells sold, not the entire battery, just the cells. And if you look at it at a price point, that's about 105 USD per kilowatt hour at the cell level. So the materials and everything that goes into it, that's 105 USD per kilowatt hour. Now again, 60 kilowatt hours is the size of a Model 3 battery from Tesla. And if you have 1 gigawatt hour, then you have close to 17,000 vehicles. This just give you a sense of what this number means. And look at what happens when you go 10x, which is easily possible. When you get to 2,800 gigawatt hour, 2.8 terawatt hour, you're suddenly talking about $182 billion just for the cells. The size of the batteries will increase, the cost will come down, but it is an enormous opportunity in the marketplace. And if you take a look at what's happening now, we look at just looking out for 2025, which is 3 years away, plans are incredibly aggressive. These are announcements by automakers and their battery partners to set up capacity to build up plants in North America and in Europe. Why do I bring these two up? The majority of the production today is in China, and it will remain in China versus any other region. However, the rate of climb in North America and Europe is enormous, which means that there are billions of dollars being spent on equipment and getting materials in place, training people. All of these things are happening right now. And the amount of growth is just phenomenal. A lot of it is happening, say, like Blue Oval is happening in the Midwest. Same thing with Ultium cells. But Stellantis and Samsung decided they would set up a plant in Windsor, Canada, just opposite Detroit. British Volt has not named a place, but they'll be in Canada. So there are a lot of different places where you can set up electric vehicle manufacturing, and the batteries go where the manufacturing goes. In Europe, they have a lead on the United States. They've been doing this for about 2 years, setting up EU Commission money. There is a ton of grants. There's ESG compliance regulations that are in place right now for these things. There are ways to, the enforcement is going to be done. There are all sorts of interesting things that are happening in the general industry. So this is very real. And if you look at how much the mix is in 2025, it's gone from basically being an almost entirely China dominated industry with the gigafactory that Tesla has at 32 gigawatt hours in Nevada being an exception, to in 2025, if these projections hold true, and there's every indication they will, you're looking at a mix where China dips below 45% and the other two combined are 55%. There are so many interesting things to talk about just on the market. Let me just tell you that what I do is I pull together estimates from a number of different sources so that I can do a cross-check to get closure on the calculations. There are a number of different sources that you have. And at the end of the day, if you want to get past data, that's easy to do because you can simply get that from IEA and other sources, updated things from the Vehicle Technologies Office at the Department of Energy. What I do is everybody talks about an exponential growth, and here it is. If you can follow the arrow here, that looks exponential now, doesn't it? And that takes the 2020 to 2030 slice that you see right here and stops. In reality, what we're doing is we're going from a transition from ICE to electric vehicles. That's a market that's finite. So it looks like it's climbing very steeply in the beginning, but it's going to hit a saturation point. And the only reason that you see a slight curve here is that the fancy predictions for vehicle growth are all linear growth year over year, the same percentage every year. And I just take that and put that into my model, which is a sigmoidal curve model. I use a sigmoidal and I modify the parameters to get predictions of what's going on.
Ron?
Yes.
Do you want questions at the end or as you go?
I'll take one now. Go ahead.
Okay. You looked at this growth. Do we have the electrical infrastructure here in the United States to charge all these batteries?
Yes, we do. We have the electrical infrastructure to charge them. That is a very good point, though, because we don't necessarily have it. We don't have the deployment of actual DC charging capability everywhere in the country. And there are line items in the budget, I think it was over $1 billion that's allocated just to EV charging infrastructure. And that's just to get the lowest hanging fruit places populated. So near major highways and intersections, the next most challenging thing will be to get that infrastructure installed in secondary roads, places where the population density is lower. That's probably the real challenge, not whether the power capability, generation capability is there or not. The other thing is you want to ballast your energy use. So these sites that have chargers generally do not have batteries on board, but there's a use for batteries at these sites in order to store the energy for peak hours, because not everybody's going to charge at midnight or 2 in the morning. So there are other reasons to have batteries at certain sites. And yet, if you're charging overnight at home, you're fine. So that's the kind of thing we're talking about. There are a lot of details around this. How big a connection, how many amps can you get connected to your North American 120 volt line? You know, that's another question. You can get 2 40 volt lines with the same amperage in Europe, and you'll do better. So I'm gonna say, you know, there's a whole lot to answer here. I probably can't answer more on the charging side at the moment. And let's move on to another part of the story here, and that is, can the supply chain keep up with the growth? When we talk about all this growth, how are we going to manage that? There are so many materials that have to keep up with this growth. You look at lithium and nickel as two of the most important ingredients, at least when we're talking about the high energy density batteries. Nickel is used in the cathodes as a lithium nickel oxide, and it's mixed in with other metals, but majority of the transition metal mix in cathode active materials is nickel. So these are some very critical things. Lithium is obviously going to be in play no matter what, or it's not a lithium battery. And of course, copper is very important because as a current collector, it works extremely well. And this also includes things like bus bars in this particular analysis. And if you look at it from point of view of the sigmoidal curve, you might follow this curve overall, but when you start looking at the minerals, you see some weird things happening. You see the nickel kind of climbing and it peaks and comes back down. You see the red line here, peaks, comes back down for the nickel. You see the overall amount coming down. You see with the purple line, you see manganese climbing up. And the reason that if you have the long-term outlook for minerals, and the reason it's difficult to say you just invest in a lot of nickel and invest in new mines is because the future of batteries is not necessarily going to be nickel. It's the cathode chemistries are changing. Manganese is very important because it's less expensive, and more important than that, it can hold 2 lithium ions per manganese atom compared to nickel and cobalt, and most others can hold only 1. So the being able to hit the higher valence state and reversibly with the electrochemistry at a good potential is all part of the story here. And the high voltage cathode materials are manganese, and that is why you see a decrease in the long term. And my projection, this could be dead wrong, but at least you can have a view that incorporates some of the cathode changes. And we'll talk a little bit about some of these changes in a bit. The other thing to keep in mind, when you look about nickel supply, is how long it takes to get nickel from discovery to validation as a nickel sulfate. Now, those things take time too, and that's one of the problems with the industry in general. There hasn't been enough investment to meet the growth that's expected. This is kind of a comparison that I'll leave with you to take a deeper look later, but it gives you the high-level trade-offs that you have when you look at lithium iron phosphate. So you have iron and phosphate, which should be very inexpensive. Yeah, sure, but also has a limit because it can only hold so much lithium. You just take the formula mass of the compound. You have 1 equivalent of lithium in there, and that's basically how you calculate it. Use a Faraday constant to calculate the milliamp hours per gram. And when you make cells, you talk about watt hours. You really don't talk about it until you make the cell. So this would assume it's against for example, a graphite anode. So there are a lot of implicit things here as well. But if you get a general idea of what the trade-offs are by looking at this kind of a curve, this kind of a graph. And there's plenty of lithium in the world. Lithium is not unplentiful. It's not as plentiful as silicon, which is interesting, but it's certainly, and these are orders of magnitude. Silicon in the Earth's crust is the most abundant material that's not oxygen. And you have, orders of magnitude more scarce. You've got other items down here, but none of those need to be battery materials. Manganese is relatively plentiful as well. Nickel and cobalt, less plentiful, but not impossibly so. A lot of the reason that the cost of things like cobalt are higher is because of the way where they are and the access in the world. So lithium is not in itself truly rare. If you look at recycling of batteries, that's another possible source. There are a lot of companies that have sprung up to do recycling. You may have heard of Li-Cycle or Redwood Materials or Ascent Elements. These are some of the companies in North America, and there's a handful already operating in China, and a number of companies that are converting from lead recycling, like Ecobat in Europe. They're turning their attention to lithium. But the real deal here is to take batteries that are retiring. So, here's your production of batteries. Well, if you put a 10-year lag in the curve, in other words, just take this curve and shift it over by 10 years and see what kind of percentage you have compared to the year that you're introducing it. Recycling doesn't look too great until, you get maybe to 2035, it could become somewhat significant. So as a pipeline for raw materials, it doesn't look so great. And most batteries are going to last longer than 10 years, it seems. They're going to have a second life application, for example, for at least another 10 years. So a 20-year life on a battery could really mean that recycling EV batteries is not really a great business. Yet there are a lot of companies that are doing just that, talking about that. The real use for EV batteries, the best use is to put them back into EVs by remanufacturing the battery. And the next best use would be, and next highest value would be for automakers which get traded in EV cars or crashed vehicles and take the batteries out and sell them to utilities. Utilities actually want them now. That's another change that's happened only in the last few years. They used to be kicking and screaming about using batteries instead of gas peaker plants. And then you have, as a last resort, you can reclaim the metals, but the metal value there is about 15 USD per kilowatt hour, and you might be able to get, triple that, for remanufacturing, maybe double that for second use. And it doesn't make a whole lot of sense to go that route, but there are lots of companies doing it. This is an example of the value chart, and recycling is probably not going to help in the long run. So what's happening in the industry? Why is there so much change? Well, the competition among EV makers and battery makers is fierce because the market is just starting out. In a nascent market like this, to get EV market share is probably the lowest cost it will ever be. So they're all after it. They want it now. And if you look at the progression of cathode materials and how the energy density has progressed is one measure of the improvement in terms of this is actually specific energy watt hours per kilogram. You can see that having nickel, manganese, cobalt oxides that were 111, that was kind of the Gen 2A because lithium cobalt oxide was the easiest one to make. It was very easy to make. You can take cobalt powder and oxidize it and lithiate it very, very easily in a two-step process. NMC 111 is almost as easy because it's an equimolar amount of each of these, and bang, there you go. Very easy to make material. So that's kind of the starting point here. And as you see the nickel content coming up, the first digit is nickel, the middle one is manganese, and the third one is cobalt. As the nickel content comes up, the energy density comes up, and there's a lot of reasons for that. We can talk about that as a separate thing too. That's a topic all unto itself. Nickel is a great thing because it's very labile in the crystal and gives you a lot of access, gives to the lithium that's in it, that it contains. And you can get more lithium out of a nickel oxide at a given voltage than you can with some of the other oxides. That's why you see things climbing as you go to 80% nickel. And there are today 90% nickel formulations as well. And these things are all happening. But ultimately, if you get to really the next set of generation products, you get to high voltage cathodes that are manganese based and can hold twice as much lithium per transition metal atom. Suddenly things really ratchet up. Plus they operate at a higher voltage, and the amount of watt hours that you have in there is the amp hours times the volts. So if you bring up the volts, you also increase your energy density. There are many ways to benefit. How does that translate when you look at battery technology and the chemistry? Well, it used to be, this is probably a high number for 2021, actually. This is one of those things that came down when nobody was looking. It was probably more like 105 USD per kilowatt hour in 2021, just last year. And the bulk of the cost is almost always has been, almost always will be the cathode material. So you can see that even though the percentage goes up, as you go up in nickel content, it must be that the nickel cost has come, the cathode cost has come down with nickel-rich materials, and that is absolutely the case because you get more kilowatt hours per kilogram of material when you use these nickel-rich materials. As you get to the high voltage ones, you can see the prices can drop down to 50 USD per kilowatt hour from about 105. That'll probably be in the 2030s. But this is the transition. This is the direction that people go. Do people want to make this change overnight? No, there's more incremental changes. And that's why you see the amount of nickel creeping up from 1/3, this would be a 3, 5, 6, 80%, and now 85%, 90% nickel. And when you do, the milliamp hours per gram, milliamp hours being capacity per gram of cathode, go up. And your utilization of the material, the utilization of the lithium, the charge in the material keeps going up. And effectively your price, which might go up a little bit on a kilogram basis, it goes down overall when you start multiplying it into a USD per kilowatt hour basis. So there are some real advantages to advancing the chemistry. So what else are they doing here? They're also looking at anode materials. Anodes take up a lot of space. Graphite is not that dense. It's got a density of about 2.2 grams per cubic centimeter, and it's fluffy because there's a lot of space in between the graphite particles. And as a result, you have like 70 to 80 microns of graphite in an anode. And if you move over to silicon, you can reduce that to 15 to 20. That's a reduction of 50 or so microns in a cell that's about 150 microns total when you've got the anode, cathode, separator, and current collectors. That means you can reduce the thickness of your electrode to 2/3 reciprocal, so you've just increased the energy density by 50%. And this is the big hook and why people talk about silicon anode replacing graphitic anodes. When you have silicon anode, you can go to 900 watt hours per kilogram instead of the 600 when the cells are fresh. However, there are challenges, and we can certainly get into that. The silicon expands, and all these companies that you see here are developing methods to keep the silicon from over expanding, because when it does, it's brittle. Lithium goes in like a sponge, expands the silicon, but it's not a sponge, it breaks apart. And as it does, it creates all this extra surface area, all these passivation layers form on it. There's a lot of interesting things that go on just from the electrochemistry plus the physical chemistry, and the electrolytes can be modified to help accommodate this as well. But all of these companies are looking at how to improve the cyclability of silicon. So even though you might get a great first cycle, it's going to nosedive very quickly unless you do something to prevent that from happening. And there are many different approaches that some of these developers are taking. I happen to be working with a company called Farad Power that has an approach very similar to Group 14, where they've got a hard carbon that gets formed around silicon particles. And there are all sorts of interesting things you can do. We have a subtractive process to alleviate the stresses in solid silicon forms. The particulate ones can be feathery, and that therefore the way they expand is not the way they would be in a bulk form. And if you get small enough in form, then you get quantum confinement. And that's what people are talking about when they talk about quantum dots. And there's some developers who take that approach very seriously. If we look at carbon nanotubes, these are additives that most people think are in for improving the electronic conductivity, and they do, but that's often not the main reason that they go in. The main reason is to improve the integrity of the electrode as it cycles, especially for silicon. As it expands and contracts, the particles lose contact with each other. These things help you maintain contact with each other. So they help hold everything together to various degrees. A single wall carbon nanotube is probably the most effective thing if the diameter of this tube is less than 10 nanometer, and there are such things out there. If it's much larger, then it probably won't be a whole lot better than some of these multi-wall nanotubes that are made through the rolling process. All of these are available, by the way, and they're used not just in anodes, they're used in cathodes to extend battery life. And some companies like LG Energy Solution have LG Chemical, the related company that they split from, make these things in-house. That's how important some of these ingredients are, and how well they connect to each other really can tell you how well the active material will bind together, stay bound together, and so will cycle a longer period of time. There's a lot going on here as well. And of course, you do get more electronic conductivity through some of these networks, especially if the particles are touching or almost touching. They actually don't even have to completely touch. You have a lot of solid state battery technologies that people talk about. The difference here is you're not using an active material in the anode in most cases. It's not necessarily true. You can have a silicon anode that has no liquid electrolyte, it has a solid state electrolyte, and technically that would be a solid state anode as well. However, by and large, solid state materials tend to be anodes where you're plating lithium. Here's an exception right away. Solid Power actually has material that is silicon-based material in the anode, but other companies like QuantumScape, they have something they call a no anode because they plate directly onto foil. And this is ionic materials, which has a polymeric solid state separator technology. They have polymer that conducts the ions pretty darn well. And all of these have pluses and minuses. This QuantumScape one uses a wafer ceramic made of LLZO, lithium lanthanum zirconium oxide, aluminum doped. So it's very specific and a hard material. It defeats dendrites. Lithium can grow and plate, but it forms needles if it's non-uniform. And those needle-like dendrites are like tiny pins that, even though they're soft and they can't really penetrate on their own, the growth of the dendrite eventually wins out and penetrates through softer materials. And if you have a material like this, which has probably 30 gigapascal Young's modulus, something like that, it can maybe resist forming a hole in the separator over the course of 10 years. At least that's the approach. These are better ionic conductors. You can make them thicker. Well, there are many different approaches here on solid state. There's no way we can cover everything that's here, but they generally fall in 3 buckets: ceramic style, like QuantumScape; sulfides of different kinds, like solid power, and many others. Actually, it's probably the most popular kind; and polymer type, like ionic materials. When you look at the ionic conductivity, this is probably the part of solid states that's best developed, finding something that will conduct lithium ions well enough. And usually these things are done by using Arrhenius graphs like these to assess the activation energy of the ionic transport, because it's all about mobility. In liquid-based systems, you would relate mobility to viscosity of the liquid that's the ion carrier. But here, you're relating it more to a diffusion-based mechanism. And even though, in principle, and proven 100 whatever years ago, that they're related, the truth is they do have 2 separate mechanisms, at least in ionic transport. If you take a look at the trade-offs here in the general buckets, you can get some idea of where this is all going. There's also the electrochemical stability window. That means on this side, you're worried about reduction with lithium, and on this side, you're worried about oxidation with whatever you're using for your cathode. And as you get up to higher voltage cathode materials, you can see the choices winning down. And some of these materials that you see here on the sulfide category don't do very well in terms of being stable for either reduction or oxidation. So these are some of the reasons that you have multiple compositions in solid state electrolytes. But again, this part of it is probably the best solved part. The dendrite growth and cycling part is the part that's probably least developed. This is an example of a generic LLZO separator. These are some configurations of the sulfides, and you can see there's a lot of material science here. In fact, the materialsproject.org is a great place if you want to see exactly what some of the electronic bands are for these things. It can be a semiconductor if there's a good band on it and still work pretty well conducting ions. Can we tell who's going to win this thing? Absolutely not me. I can't tell who's going to win. There's so many variations out there. They have pluses and minuses. Some of the minuses are commercial scale up. You have very disruptive materials in some cases, very disruptive processes to make these materials. And that alone is going to create a lot of time where competitors can continue to make progress with other solutions. So you don't necessarily, you might have a great system in the lab, but it might take you longer to implement it. Or maybe you're lucky and you can get it both ways. But it's very difficult to tell at this point who the winners will be. And there are many candidates, as you saw. What other kind of things can we do at the battery level? And so far, we've talked about that. But it's 2022, and it's about time that the automotive industry embraced wireless communication. I mean, we have things in the lab that we use to get data wirelessly, so why not on a car? It was a matter of getting things through SAE, the Society of Automotive Engineers, and getting consensus. But it's very difficult to build a battery management system when you've got the same ground reference voltage for the data as you do for power, because they're going to be common. And so you have to separate your high voltage from your low voltage data lines, 0 to 5. And you can fry your board if you don't have opto isolators. With wireless, you don't have to worry about that. You don't need to design those things. You can get more compact boards, fewer parts, and be totally free of worrying about opto isolators. The big change here has been that they were able to cycle through megahertz processor rates, and they're able to get the data and the parity checks and all the things you need to make sure that the data is real and heading in and actually gives you what you need when you get the new processors in place with a simple antenna on every module instead of having wires. And a single point of failure, by the way, is the two-wire system. They used to put a third wire in there. It was just a redundancy wire. You don't need that anymore when you have these wireless systems. So it's much easier to put together a battery when you have, with the electronics on board, if you don't have to wire for the data. Of course, you have to do the power, but you don't have the data, and you don't have to worry about the crossover and frying boards. So this is actually an interesting thing. There's also a lot of innovation on just how you produce the cells. Just when you think there's no more innovation in rolling up a cell, Tesla in 2020 announced that they were going to develop these tabless cells. Normally, you'd have just a few of these copper tabs pointing out, and each one of them would be welded on the fly in the production speed to the cap on one end and to the can on the other. And all of that takes time, and you don't get a really good connection. So they were limited as to what diameter they could build, because most of the heat out of a cylindrical cell travels through the metal current collectors. And don't forget, there are insulating layers in between, or not as thermally conductive layers in between. The electrodes plus the separators are wound in here too. They don't conduct heat very well at all. So most of the heat comes out this way. Here you can see, instead of having just a few copper tabs coming out, the whole thing is slit tabs. So they don't coat the edge, it's a self edge coating, uncoated edge. And they carefully somehow put in these slits and run it at production speed without tearing the electrode, fold them all down, and form something that will pack into the bottom of the aluminum deep drawing can on one end, the cap on the other, and there you go. You have a great electronic connection, but you have a great thermal connection, and that's what enabled them to go from the 2170 cell, 21 millimeter diameter, to 46 millimeter diameter. So take that 21 and square it, take that 46 and square it. That's the ratio we're talking about. So that's how they're able to get 5 times more watt hours in the same volume. There are lots of things about batteries that I love. It's multidisciplinary, so you're never bored. You have clearly the electrochemistry, but you also have a lot of issues on ionic transport. That's what solid state's all about, for example. But even with liquid-based systems, flow through porous media is part of what you're dealing with here. There are tools, all kinds of tools to measure things that like EIS, electrochemical impedance spectroscopy, AC impedance, if you will. There are electronics that you just saw. There's a ton of modeling that goes with software for that. There's different schools of thought on how to do the modeling. Some of it is from thermodynamics, looking at Nernst equation and modifying it for rate. Others are simply dynamic and learning using Bayesian type filters. So there's all sorts of approaches just on the modeling side for the algorithms on the battery management system. Thermal analysis is critical. If you get a hot spot in the cell, that is the disaster that can lead to that cell failure and cascade into failure of adjacent cells. So there's a ton of thermal analysis, and that's non-dimensional. We can't do it non-dimensional. That's a dimensioned analysis. Physical chemistry, material science, organic chemistry, because of the because of the many polymers and other organic building blocks that are in binders and things like that, or modifiers for the electrodes, a ton of that. And if you go to the Volta Foundation, if you Google that and battery bits, you'll be able to find a really great document that's online, available to everybody. It'll give you a ton of information that'll be like 100 times more than what I've shown you here today, spanning all sorts of aspects of the industry, the market, and end uses, the chemistry, the material science, everything you'd want to know, with tons of references for that too. The materials project is something that's really huge in terms of coming in and explaining properties of materials from computational calculations, a lot of DFT calculations that tell you interesting things about materials that are used in the battery realm. Of course, it can be in other applications, but it's very useful in the battery realm. There's a Argonne National Lab spreadsheet it's actually called BATPAC, and it is a comprehensive estimate of everything that goes into the plant, materials and its OPEX, the cost of energy. You can put in all these different variables and you can modify and tailor it to whatever you want. The CapEx is included, and they also publish articles deriving the changes in the base case from year to year by Argonne National Labs, all paid for by our good old tax dollars and available for us to use if we wish to do it. There's a great organization, the North American Battery Organization, NatBat. Its membership has just been swelling with the emergence of the battery industry in North America, and they have a lot of resources to offer as well. They have a newsletter that comes out every week, and that alone is a great way to track just the incredible amount of movement in the industry. So thank you very much. Oh, there are some trends. I'm just going to go through a little bit of these trends because I know we're getting on with time here, but one of the important things is that auto OEMs are realizing how much money they can make, but how much money they save by putting together an ICE versus an electric vehicle platform right now. Incrementally, it's less expensive to put together an ICE because of the fewer number of parts and the less manufacturing floor space it takes, lower gantries, for example, even for the cranes, just to put together the EV platform. And if you look at the plant that Volkswagen had in Zwickau, Eastern Germany, that plant was a traditional ICE plant that maxed out at about 120,000 vehicles a year. They changed it up on the fly, and they are anticipating to 150 or 160,000 EVs a year, the ID3 and ID4 vehicles, out of that same plant without expanding it one bit. Just that sort of thing. There are examples beyond that, but that's one of the best known in the public domain. Other companies are just building greenfield plants. So, but that one was a conversion. The supply chain is tight, as we mentioned before, it's really interesting to see that even automakers are looking for offtake agreements for these things to secure the right to nickel and lithium, sort of as a futures buy. They won't use it directly themselves, but their battery, whoever they buy the battery from, will have to buy battery materials, and that's how it will enter into what's earmarked for them as cells. They're trying to secure the supply chain that way. It's just an incredible thing to see. I'm not going to go through every one of these points, but keep in mind that there's a lot of tension between automakers and EV makers, because EV makers have really said that they want to make their own cells in-house, and they've admitted that they just can't because the market's too tight and it's climbing too fast. They don't want to miss an opportunity, so they're forced to work with them. How do you think that makes battery companies feel? Well, so battery companies have done their part in trying to secure the upstream raw material supply chain and turn that into an in-house process, so they're hard to swallow in the future. But in reality, they're kind of working together, and you can see that with the different partnerships that are happening in North America and in Europe, and also in China. There are quite a few interesting developments there as well. So I certainly don't have the time to get into all of that. I don't thank you for your patience. It's just always difficult to know what to include, what not to include when talking about batteries, because it just washes over so many different walks of life. Momentum Dynamics is interested in batteries as well here locally, because even though they're powering batteries wirelessly, that's opportunity charging when you don't have to plug in, when you just have to hover over a coil, and you have a coil in your car and a couple, then it's very convenient. You don't have to worry about planning to plug in. You don't need a person to actually do that either. And that's one of the advantages of that. Farad Power, making silicon hard carbon materials that the objective there is to do what everybody else's objective is, to cycle longer. New Dominion Enterprises is making a phosphazine-based electrolyte solvent for lithium-ion liquid. Phosphazine is a non-flammable liquid. So this is an advantage when you're doing cells today and you want more safety. You can relax the thermal management, for example, take away the space that you need for it, take away the cost, and there's another value for it there. Plus, it's compatible with both lithium and metal. How many liquids do that? and it's compatible with high voltage cathodes up to 5 volts. Nanaloy Energy has a process to deposit some unique compositions that really enable some anode structures to be made for solid state. There are other applications for it as well. And Honeywell, you know Honeywell, that's a huge corporation. Honeywell is making a transition going from serving the pharmaceutical industry as based petrochemical and paper making, and really doing as much leveraging of the technology for their manufacturing execution systems and metrology, and putting that into lithium ion. And that's also enjoyable to work with them. So thank you very much for your time and your attention. I know we went all over the board, but there's a lot going on, and appreciate your time.
Well, thanks so much, Ron. Incredible amount of information, and at least to this organic chemist, boy, there's an awful lot to learn. So I think I'll stay in my lane. We have a number of questions that have been submitted by chat, which I will read to you. Actually, there was a comment before about making the presentation available today, because there was a lot of information, and I guess that's a question for Joanne. So hopefully we'll be able to get your presentation up on the web.
I'm happy on my end to do that.
Good. Okay, in terms of questions from Peruzzi, that's Robert, right? I think Robert Peruzzi. He's asking, are you a forensic engineer expert witness, or are you interested in that sort of consulting? Consider joining the National Academy of Forensic Engineers website. And he gives the website.
I think that's an intro, Ron. I think that's the question of consultants' information.
Yes, that's in part of the, instead of the elevator speech portion of your meeting, that was my comment.
Oh,
okay. Very good. Yeah.
Can people read what I am, the chat page that I have on the screen, or not?
No.
No?
Let me stop share, and maybe that.
Okay, can people see this?
I see you.
Yep.
Okay.
You have to click on the bottom where it says chat, and then it'll come up for you.
Okay, thanks. Go ahead.
Is that directed at me?
No, that was directed at anyone who wants to see the chat.
Yeah,
Okay.
I can see the forensic comment was first, and the next was one from Michael Bigwood.
Right.
Oh,
Michael
that
Bigwood.
looks like an introductory comment also.
Need polymer synthesis lab work done. Look, Michael up. Question from Joanne. Do you know of any plans for manufacturing in the Mid-Atlantic region?
I do not, but there, it depends. If you want to extend the North Atlantic region to North Carolina, that's a push. But if you do, there's a Samsung plant that's being planned for that location, Samsung and Toyota. So I don't think they've chosen an exact town for the major plant for that, but that's as close as it is. It is an interesting question. I think there aren't many plans to put up big factories in the Northeast. They're generally going where there are, the Midwest, for example, or in Nevada, there's a gigafactory, Texas, another gigafactory for Tesla, Core Power in Arizona. There's actually a map that I can supply with the different places, and none of them are really Mid-Atlantic, unfortunately. I think the energy cost is a consideration for some of these. That's why, for example, the Stellantis LG Energy Solution plant is going to be in Ontario, because Ontario Hydro is offering an introductory low rate of energy. And a lot of these operations, they need electricity to run. So that's one of the considerations on locating a plant.
Yeah, actually, after I typed that, I wished I had said, the general East Coast region and, somewhat inland as well, rather than just limiting to the Mid-Atlantic. So yeah, I'm glad you brought up North Carolina. Thank you.
Yeah, actually, there is one in New York State. Binghamton University, formerly SUNY, is where Stan Whittingham he teaches. He was one of the 3 people who won the Nobel Prize in 2020 for the for inventing the lithium-ion battery. And so that Binghamton University has a company called C4V, which is affiliated with another company called Imperium 3. I know these sound off the wall. They're not Samsung and those kind of names, but they have a facility that they're planning, a gigafactory that they're planning in the Binghamton area. And it could grow into a larger plant. I think that might be the nearest large plant that's planned. There are a lot of startups in the Boston area, 24M, for example, quite a few others actually. But I don't know of any major plants that are, in our immediate environment here in the around the Philadelphia area, or even within 100 miles or 200.
Thank you. Mike Bigwood has a question. I might know the answer to this, but I'll defer. A lithium ion has a physical size. Where do we stand today in terms of battery capacity with respect to the theoretical limit?
Well, a lithium ion has no electron and in its outer orbital, which is why it's small. So it's very energetic and relatively electropositive, and that's the reason that if you look at the electrochemical series, it's near the top. It's 3 volts over hydrogen, the standard hydrogen electrode. So it is very tiny, but when it gets intercalated into a crystal, and this is where the materials project actually could be very useful, because they can show you the densities of and the density of state functions for these things. But if you take a look at that, you'll see you're packing it in pretty much what you would expect for the energy levels that are available as calculated by like DFT calculations and things with different models, force models. So you can actually get, you're not going to get a lot better than some of these empirical estimates and modeling, I think.
Let me ask a follow-up question on that. So lithium is about as small an ion as you can get, but if you go down the periodic table, there's sodium, and which has the advantage that it's much more readily available. Is the problem that it's a much larger ion?
The problem that we're trying to solve is, with energy density, it's really the charge per atomic mass, and that's what you can't beat. I mean, that's just the table. That's just what makes lithium. And that's you can't get around that. We're living within the confines of the periodic table, the electrochemical series, which is a surrogate for electron affinity, electronegativity, those kind of things. That's what we're living with.
Okay. Here's a comment from Suzette Schultz. Wow, lots of information. Would definitely like to watch it again. Beyond battery storage capacity, is there an issue with heat generation, and how's that being handled? You touched on that a little bit. And let me add to that question. So I don't want to take away from Suzette's question, but she's asking about heat. And I also wanted to ask about the reports that you hear every so often about lithium batteries catching fire.
Yeah, and they're related. Well, the heat generation comes from, you have a driving force and you have a resistance, and anytime that you have that situation, it's unavoidable unavoidable to generate some amount of heat. You just can't transport things without generating heat. So the real question is, if you do it very, very slowly, then you generate less heat. The closer you are to thermodynamic equilibrium, less heat you're going to generate, but it's useless. So what you measure of that really does come down to impedance, and usually it's the ohmic and real component that matters when you're generating the heat in these ways. That would be the batteries are DC. So you're talking about the ohmic generation. I squared R still works. So the current squared. So in this case, it would really be the current density. That would be the flow of charge per unit area per unit time. Gives you, because it's in that vector, in that direction, that'll tell you how much heat you're generating based on the resistance, that is I squared R. One of the issues that you have in batteries is that if you'd like to increase the energy density, normally you'd make the electrodes thicker, but that means that your ions are going to travel farther. And if they do, then resistance is linear with distance traveled, and the heat generation is also going to be dependent on the loading. So it's as you double the thickness of your electrode to get better energy density, you're going to go 4x on the amount of heat generation that you have per unit area. So that's the intrinsic problem, and there have been good articles written about that, and that's why almost all the electrodes that are out there, because they have the same porosity and the same electrolyte with the same conductivity, ionic conductivity, they generate about the same amount of heat no matter what you do. So they all kind of ended up in the same place. When we started out at Lithium Technology Corporation, we thought we could make thicker cells, thicker electrodes. And so we always end up in the same place. And everybody else was discovering the same thing. So now there's some articles that show that polarization, the concentration profile in the electrodes, almost always works out to have the same value. And that's the limitation. So you hear loadings of 3.5 milliamp hour per square centimeter. That's about as much stuff as you could put down there and still expect it to discharge at a C/2 rate, in a 2-hour rate. So these things are all rate related, the amount of heat you generate. The amount of heat that you generate also raises the temperature if you don't remove it. And the nickel oxides, in the structure of the nickel oxides, the bonding energy between nickel and oxygen isn't all that great. So nickel likes to switch partners, oxygen partners, more readily than, say, manganese or cobalt. So that's one of the reasons that nickel oxide was not used in some of the very first cells that were made by John Goodenough in the late 80s. It was just the risk of these things going autothermal was too high, because if the nickel is very labile and it leaves the crystal, lithium comes in and it releases oxygen, and next thing you know, you've decomposed your cathode material at a temperature of like 160 Celsius, and that's not too hard to reach. Next thing you know, you've got your own oxygen. It says, well, I just got made, but I like to be reacting with something else. There's some organic stuff here and other things. I think I'll burn something. And that's how things go into thermal runaway, and catastrophic. With lithium cobalt oxide, it was over 200. It may not seem like a big difference between 160 Celsius and 200 Celsius, but it was enough to have viable cells for Sony. I didn't know any of this when I was doing this stuff in the early days, but it's pretty clear today. That's kind of old science, established things. And what's happening to get more nickel content today is that they're actually structuring the crystals. They're making the crystals, when they synthesize the materials, to make sure that they're more stable ahead of time. And they'll do that by controlling the crystal growth structure. So crystals are not always the same structure. There's something called single crystal growth, which will also eliminate the surface area and how these things expand and destroy themselves. So there's all sorts of things going on cathode synthesis that's very interesting in the inorganic chemistry. There are actually some organic materials that moderate that. So there's some interesting stuff going on. BASF is a company that works on that with Toda America, and Umicore has done some stuff like that. They have a lot of places in Canada, in addition to their home base in Belgium, and they have a lot in Korea. But in the United States, I think you're going to see more development there. Dalhousie University and Jeff Don, who's done a lot of work with Tesla, has done a lot of work on stabilizing cathode active materials and the oxides that we're talking about right now. But when you put in manganese and cobalt, you stabilize the bonds, the oxygen bonds, to a great extent. And you don't need to have a majority of it to have that happen. And the other thing you can do is you can have non-stoichiometric crystals. And again, you go to the materials project and play with that, because if you reduce the amount of oxygen below stoichiometric, then you're forcing a valence change on the nickel, and it gives you some stability. It doesn't move around as much. So that's another thing you can use. Johnson Matthey tried to do that with all nickel oxide, for example. So there's a lot of interesting things going on. And then you got lithium iron phosphate, which is very stable too. So the reason the temperature matters here is that the autothermal temperatures are different. Lithium iron phosphate has an autothermal temperature of 290 Celsius. It's like 100 degrees over many of the others. And that's why people talk about it as being a very safe chemistry. But if you get rid of the heat, you can run anything. That's why the battery management systems are so important, by the way, because they manage thermal management and enable the nickel with the higher energy density. Otherwise, they just be unstable. So battery, don't neglect the electronics. It's important. Yeah,
Keith Wing asks about the availability of promising battery inorganics relative to the issue of U.S. national supply security. Are lithium, nickel, and copper still the elements we'll want to have 10 years from now?
There's going to be a shift to manganese. 10 years might be the beginning of shift to manganese. Argonne National Lab developed these things called layered materials that are based on manganese oxides. Instead of being a lot of the materials that we've been talking about today, the cathode active materials are layered oxides. And the stuff that was developed at Argonne National Labs on Michael Thackeray and simultaneously by Jeff Don and Dalhousie University are three-dimensional spinel materials. So instead of having layered things, they actually have a 3D structure. And the rock salt structure of the manganese enables you to bring in 2 lithium ions for the one manganese. If it's a layered manganese oxide, it can only get 1 into that crystal. And it's just, if you look at it, it's hard to explain, but the configuration is there. You can't get more than 1 in. But that gives you hope that we won't be locked into nickel, into a nickel yoke around us. There's lots of nickel in Canada, but it takes like 5 to 8 years to develop a nickel mine. It takes the same amount of time to develop a lithium mine. And so I'm worried that we don't have enough time to develop some of the things in the United States. And a lot of the time is wasted by getting permits. In the United States, you have to get a lot of permits. Less so in Nevada, more so in a lot of other places. I'm not optimistic about about U.S. supply, Canadian supply maybe.
A couple of observations. Stu Hellring writes, yes, thermal heat management is handled at various, handled at the pack level with various ways, or in various ways. In Davenport writes, a friend of mine drove from Austin to San Antonio recently. He said he was amazed at the vast size of the Tesla Gigafactory at the side of the new highway. And Joanne Leonard writes that we will publish the video on our web channel, and you can see what the web channel is from the chat. Here's a question from Stu Hellring. Will the type of CNTs in anode make recycling more difficult due to their inherent toxicity?
They're very long. The ones that are being used, they might be less than 10 nanometer diameter, which kind of makes them a hazard, airborne hazard, but they're also very long. And they're like some of these things are 100 microns long. And that's a big aspect ratio. And what happens is they're flexible with that kind of aspect ratio. And the van der Waals forces of the surfaces of these things tend to make them flock together. And so one of the safety things here is that you can't really get a lot of individual things that you won't see airborne. In fact, that's one of the problems is dispersing these things. It's very difficult to separate them from each other. So you have a company like Oxial that's making their product name is Tubal. So they're making these things in dispersions because the battery companies are going, what do you expect me to do with this stuff? It's it's not, if you do something like if you do somehow inhale or ingest it, that's not good. But it's not a common liability in normal handling if you handle it properly.
Okay, I think those are the questions and comments. A lot of information, really stimulating. And thanks so much, Ron, for agreeing to present. Any last words, perhaps from our chairman?
No, our next meeting is May 11th. It's a talk on toxicology. So please register, and we will have the information on our website shortly. So look
Very
forward
good.
to the meeting in May. Thank you, Ron. It was a great talk.
Thank you. Very, very nice to be here. Thanks to everybody for attending.
Will your charts be available? Can we get those, or?
I will certainly make them available. And I think Joanne said that she would be looking into that as well.
Okay, thank you. Okay, thank you, everybody.
My pleasure, everybody.
Have a good night. Thank you, Ron, again.
Bye.
Hated it. Awesome.